But we can do more things. So this holds, but we can also do things that are very unpleasant. For instance, we can say, oh yeah, and here, maybe let's write that down, this is r equal to 6. If we do a check here, we check according to this definition. So we take a minus r, we take 42 minus r minus 6 is 36, right? And now what we have to do, we check 9 is, of course, divisible by 36. Everything's fine. Okay, so again, this was really easy and naheliegend, obvious. And now comes something that's not that obvious. For instance, what happens? We can also write this equation equal to t. Okay? And now my claim is, meine Behauptung ist, okay, from this it follows that the r is equal to 15, which is kind of strange, right? This is not the rule. Let's look how often the 9 fit into the 42, because it doesn't fit in 3 times, it fits in 4 times. What I'm just telling you here is, this equation still holds, right? Das ist 27 plus 15 is 42, that stimmt, right? So now we're going to look into the red box and look whether the definition holds. The check here is, again, we take 42, we subtract 15, which is 27, right? And now we have to check, does 9 divide 27? Of course it does. So what I want to see here is 200 faces that look a little bit confused, right? Well, what I just showed you here is the remainder is not unique. Okay? Das ist nicht eindeutig. According to this definition, there are many remainders. I'm going to show you now things that are worse. Okay? But also, so here I went down, right? I subtracted 9 less, now increase the number of 9s. I say, okay, I do 5 times 9, that is 45. And which integer do I have to write down here so that this equation is fulfilled? So this is a true equation. You can use pocket calculator, iPhone, cloud computing. What do I have to write down there? -3, very good. So according to this statement here, the remainder can also take the value of -3. Let's go back into the definition. Check. 42 minus -3 is +3. So this is 45. And again, we have to check, does 9 divide 45? Of course it does. So the big lesson learned here is the remainder is not unique. So this is we're going to talk about equivalence class and equivalence classes. Let's first start with another set of examples that are somewhat smaller examples. A equals 12, m equals 5. And then what we see is that 12, this holds. This is kind of the normal thing, right? We look how often does the 5 fit into the 12. 2 times, we get a remainder of 2. But then we do the same funny thing here. We can also do 12 is also equivalent to 7. We can also go into negative numbers here. Minus 3, if we do the check here, we have to look 12 minus 3, which is 5 divides 15. It works. Okay. So, and now we come up with a definition. The set, and kind of in the beginning we start with 2, 7, and in this direction it's minus 3. And what do those three numbers have in common? What is the distance from here to here? That's 5, right? And that's also 5. And you can continue that as a series. So this is 12, 15, and so forth. And also you can go into in the negative range here of numbers. So we look at this set. This is an infinite set. Danke. Okay, 17. So forms an Gänsefüßchen equivalence class. Modulo 5. And now comes the important additional sentence. All members of the class means all the numbers, all the elements that are in this class, everything that's in the curly brackets in den geschweiften Klammern here, all the members behave, bad job cleaning the board, behave equivalent modulo 5.